Okay. So, recording this just for those of you who are not here. Yes. Potpourri in terms of with
in terms of what I saw in the list.
Yeah, this is potpourri. A mix of things which, yeah. Okay. So to wrap this up, I just wanted to do a few comments and then do a Q&A, and that's why I wanted to remember to record this part on the final project. Make sure that the expectations are reasonably clear. So again, your final project is really about, well, there are some particular concrete things you have to do, mostly about demonstrating that you have gained some understanding of the fact that there are an enormous number of possible things you could build that are a computer, and there are trade-offs among them. And anything you actually want to build ultimately is for some particular optimization metric, which is specific to your deployment goals, and that you might take different parts of the design space into more or less consideration, depending on what it is you're actually trying to do. Right? So for instance, if my optimization metric was just latency, I want to make my latency as small as possible. I do not care about energy. I do not care about area. I do not care about cost. You will build a very different processor than if your optimization metric is just energy. Right? Now, no one really has just energy or just, but you can imagine that the other things have been sufficiently small. So imagine the processor in your watch, not your smartwatch, your watch, like your old Casio watch, right? Where the chief design metric is, I want this battery to last 3 to 5 years, right? It needs to be able to update a second timer once a second. Yeah, other than that, I'm good. Performance, not really one of my chief design goals. Yes. They work mechanically. Springs, windings. Yeah. Anyway, so for this project, here's what you're going to do. You've been given two particular design metrics, right? So one is the EDP, energy delay product. The other one is the energy delay squared product. If that doesn't mean anything to you, here we can do some very simple units. This is joules seconds, and this is joules seconds squared, right? Lower is better for both. Remember, the goal is not to melt and be slow. The goal is to, be efficient and fast, or to be very fast and somewhat efficient, right? Now, given these two metrics, you've also been given a constrained design space, right? So you don't have to wonder whether or not, doing ands in the middle of your DRAM is the choice for you. That's not part of the space. You're just looking at a single core processor with a set of 18 knobs that you can tune. Some of them only have 2 settings, like in order, out order. Some of them have many more, like your cache configuration, right? If you do some very simple back of the envelope approximating, if you assume that basically on average there were 4-ish options for each of these 18, and you'd expect that to do something like 4 to the 18th potential different things that you might have in your design space. It's not really that, because there, well, again, aren't actually 4 of each, et cetera, et cetera. But the short version is there are a lot. That is all that matters. There is a fairly large number of potential designs. Even if you start getting rid of the ones that are invalid, because not all the cache configurations are actually valid, it is more than you would want to go and search in its entirety, right? So the goal is, of the project concretely, right? You're going to only build 2 functions. So function 1, validation. Is this a valid configuration based on the specified project constraints? All right, now some of the project constraints are enforced already for you, right? Your TLB latency is not one of the free parameters. You don't need to check it, right? Things that are already done in the run script it's built on, you don't need to check. You need to check the things that are not actually orthogonal in those 18 dimensions, right? Like some of the cache parameters where we have specified at a project level that certain sizes have certain latencies. So check that they are in fact set properly. Some of them are enforced because the simulator will refuse to run certain configurations, like where your L1 is larger than your L2. It'll just say nope, and that'll be the end of that, right? But those are all included in the project spec. Okay. Once you can validate that the configuration you were attempting to ask the simulator to provide is valid, then your job is to pick one at a time 1,000 of those points to sample. Right? The framework will remember all the details of what happened for you. The framework is already set up to, for any configuration that you give it, it will run those same 5 benchmarks that you ran for reading assignment 1. It will compute these metrics based on internal tables. It will record that, and information is available to you for any subsequent pick that you want to make in exploring this design space, right? And it will log it, which will be the final output that they will then use to produce some graphs at the end. So all that has been done for you by the framework. You just need to pick which 1,000 unique, valid configurations you're going to explore. Yes? No. So one run of the program will run 1,000 evaluations. You are writing a piece of code that will generate every time it is, so there's a function that's called, and it's get me the next configuration, right? So you build a validator, so there's a logic in there to check whether or not the configuration that you're attempting to use works. You may also wish to use this yourself before you attempt to pass it into the rest of the system. Otherwise, it's going to just ask for another one again, right? It calls this function and checks. You're running your own validator. It's short. It's a series of if statements. If the L1 is larger than the L2, no, right? Just basically go through the project spec. Yeah. So it will be reasonably apparent to you when your validator works because the simulator will stop crashing when you try to run it. And the data that it produces will not be 11 orders of magnitude off and weird and otherwise inscrutable because you wandered off the end of a table with invalid configurations, right? So if you look at your output logs, it will be very, very obvious when your validator works, right? Okay, so the more interesting part of this, right? So why do I have you write a validator project function? Because otherwise you won't read the spec. Right, this is not intended to be hard. This is intended to force you to read the specifications. Okay, this is just like if there's no, yeah, just check, right? This is the fun part, and it's very, very open. I am not asking you to find the singular best configuration for this metric. That is the goal, but it is not the evaluation, right? What I am asking you to do is have an internally consistent reasoning that you will describe in your report between what we've learned in this class, the metric you are optimizing for, and how you attempted to explore a large space. All right. So for instance, what would you change about your exploration of the space for this metric versus this one? Right? So if you say, oh, if I'm looking for something that's optimized for joules, I'm going to always look for the maximum, hardware configuration, and I'll go, that makes no sense. That's very silly. Right? Why would you put the maximum resources if you're optimizing for energy? Right? On the other hand, if you're optimizing for S squared, I'm going to go off for the absolute minimum resource in order, and you're like, no, that makes no sense either. Right? The answer is everything is going to be a set of trade-offs. So how are you biasing your search? How are you going for building some priors? How are you constraining the space to make it smaller? How are you just biasing your sampling? However you're doing it, there is no particular right answer. There is an entire subfield of computer science about how to, best sample large non-convex spaces. You have not taken those as prereqs. I do not expect you to be doing, advanced simulated annealing algorithms or stochastic gradient descent or. That's not the point. The point is we have a set of trade-offs. we have a set of metrics. How do you encode some of your understanding right here? Now, what I would recommend, I'll get to you in a second, as an initial way to do this, you can start with the simplest, stupidest metric, which is, random sampling works for polling, right? I could just do 1,000 at random. That's not intelligent, but it would be a start, and I could look at my data and I could figure something out from there. So if you want to understand if everything works all the way through the project, my advice would be, if you don't have a stronger sense of what you want to do for your heuristic-based search, you can always start with random. Although do always remember that you need to make sure you use a new random seed every time, because some things are not valid. You do not want to have the infinite loop of, I suggest invalid thing repeatedly. Why am I not advancing? Yeah, don't do that. Yes.
So the space exploration basically 1,000 samples.
Right. So one run of the binary that is produced, named DSE, Design Space Explorer, will run 1,000 experiments. So 5,000 individual benchmarks. So each experiment is 5 benchmarks running in a particular configuration on their inputs. It runs them all, collects the data, takes the geometric mean, populates some internal tables with joules, seconds, computes the joules and seconds and joule seconds squared, makes those available to you if you so wish to use that to figure out what you want to explore next, right? So WR1 has a fixed design space that you explore exhaustively, right? In WR1, the size of the design space was 12. There were 12 possible configurations, 6 predictors times 2 pipelines, right? The size here, again, is something more like this-ish, right? It's not actually that. I have computed it before. I don't remember the number off the top of my head. Long story short, it is much, much, much larger than 1,000. That is all that is important. The way that the program framework that you are given works is it will request 1,000 unique, valid configurations, right? So if you give it a configuration that is invalid, it will ask you for another one. If you give it a configuration and you've already asked for it before, it will ask you for another one. It will keep doing this until you have given it 1,000 unique, valid configurations, right? It will output a log of the relevant statistics, right? For every of those 1,000 configurations, it will output the best configuration that it has seen across those 1,000, right? Those are in the output files. They're in the FAQ if you want to look at how to read the output files. They're comma-separated values. You can literally load them into your graphing software of choice and then just go plot, right? No grep required. Yes? Yo. Shh. Yes.
What I was going to say now, which is this closer to MP1 or WR1, like the scope and diamond acid you have to put in?
It's really sort of neither. It's pieces of both, right? So you're writing a report, right? The report requires you to run some experiments, do some graphs. That sounds very WR1. You also have to write some code to do the experiments. That is not WR1. This code is, at least potentially, much simpler than the logic you had to do for MP1, right? I mean, this, as I said, is a series of greater than, less than, table checks. This is pretty simple. This can be as complex as you want it to be, right? So this is a very open-ended project. Let me give you a sense of the longitudinal curve of how this project has been formulated across the years. When I first started teaching this class the better part of 10 years ago, we did not provide you a framework. We just said, here's a simulator and some benchmarks. Go to town. And people wrote their own scripts. They collected thousands of data points. They did fun, weird, random stuff. That was fine. But it turned out that I say 2017 or so, most people didn't actually know Bash by the time that they took this class. So maybe I figured I should help people out a bit, and I provided a framework that handles a lot of the grunt work of just running lots of experiments and collecting data. If you were hoping that you too would get to understand what it's like to run thousands of jobs and collect all the data from them, my condolences, I already did that for you. I've taken that option away from you. But for most people, they'd rather focus on something else. So this allows you to basically just read the spec, ensure that you read the spec, and go do some exploration, get some data, and then analyze the data and tell me why you did what you did and what the data finally means, right? So at the end, you're going to get some best configuration, right? This is the best thing it found of 1,000 samples. Maybe your sampling technique was not great, right? And you found something that, you know, it is what it is. Don't just say, and I found string 18 digits. Map that back to, was it an in-order, out-of-order core? How big was the cache? Does the configuration that you found make some sense, right? Everything is being normalized in the outputs to a baseline configuration that's, you know, almost the minimum configuration. It's a pretty minimal machine. Does the ratio with respect to this metric that you're seeing make sense to you? Why? Right? Do you think that your search was good? I mean, again, you don't know what the whole dynamic range is, right? But you should at least have some sort of general sense of why this might be a reasonable thing to have found given the way that you were doing your search, right? So if, for instance, you did your search, you know, where you held a bunch of things fixed, changed a couple of variables at a time, that's going to constrain your space. That's fine, perfectly valid with respect to the approach. But you should explain why then, you know, what you got still makes sense, right? So explain that you understand some of the trade-offs we talked about in the class. The write-up is the means by which most of this will be graded. I'm not going to go and run all of your design space experiments again. That's not the point. I don't need to waste that much disk space. But you will be also, as noted, submitting your code just as an audit check to understand if something's really weird in there. Yes.
I wanted. Oh yeah, by spec do you mean what's in the instruction?
The specification, yeah.
Okay.
Yeah.
What's in the instruction?
Yep.
Or like the superscalar, scale or not.
So if you follow all of the requirements within this, everything will be valid for simple scalar, right? If you want to understand why certain things are set the way they are or what they're causing simple scalar to do when you set that parameter to be a particular value, you can go read the simple scalar user guide, right? So if you can't remember what the heck the fetch speed modifier is doing, you can go read simple scalar, where it'll tell you that it is a multiplier on the relative width of fetch to the width of the pipeline as a way to deal with branch misprediction, overfetch, et cetera. Yes. Mm-hmm. Yeah. Happy to. Okay. Let's see off of modules. Okay. Okay. So the way to read this, these are your dimensions 0 to 17. So a particular configuration is a value in each of these dimensions, right? The value specifies the index into a table associated with that dimension. So if I say that dimension 0 has value of 2, what I'm telling you is the width of your machine is 4, right? You are looking at index 2 of dimension 0, right? So every configuration is some integer index basically into this table of length 18, right? So a set of 18 indices. Now, some of these have more values than others, right? So for instance, the unified number of L2 sets has 10 potential options, whereas scheduling is either in order or out order. Your index is going to be either 0 or 1. Yeah.
So like first argument
is 0, this is 0 width is being water.
Yeah. Yes, everything is indirected through this table. Yep.
To set it, let's say I want to set like the width, I would do dimension 0.
Dimension 0 specifies the width, and then your possible values are 1, 2, 4, or 8. Right, you're going to put 0, 1, 2, or 3. Yeah. Right, these are the valid values that you could be specifying for width. Yeah. Now, this part of it here, you explored. Right, so you basically ran something with dimension 17 and dimension 2, and you ran it exhaustively for a fixed value of all the rest of these. Right, that was what was run in WR1. Right, a real processor has a much longer list of descriptive parameters. Also, a real modern processor is a multi-core. Also, a real modern processor is actually an SoC. So actually, it's a collection of different processors, all of which were independently optimized, which communicate through a common substrate with a memory system that has to serve all of them. Also, there's a GPU, which has its own memory system. Also, there's an I/O memory system for multiprocessing off-chip for one processor, one memory hierarchy, go 90s. Okay, yeah, right. Yes.
We have to run this on the Linux machine.
You do not have to, but you would be making your life unnecessarily challenging by not doing so. The framework is set up to use files that are already in particular places on the common shared file system, namely the simple scheduler simulator and all the benchmarks on all of the inputs. If you wished to copy the simulator and the benchmarks and their input directories in the particular structure that they require, and then modify the shell script that this is calling in order to run them on your local machine, you are welcome to do so. But I feel that that is unnecessary work. You don't have to go to Westgate, just log in remotely, man. VPN. Yeah, step 1, VPN. Yeah, then log on, then run screen. Because a run should take the better part of an hour, right? It's doing 5,000 experiments. It takes a little bit, right? It will take longer if you keep just enumerating invalid things or things you've already tried over and over and over again. But yeah, broadly speaking, 30 minutes to an hour, depending on the particular machine involved and how heavily loaded it is. So don't try to just go in and run this, and think that you're going to be done in 5 minutes. Do actually, sit down for a minute, go get some food, have a snack. Yeah.
So are we going? Questions.
Because it's early in the morning, it's almost the end of the semester, and there's not enough coffee in the world.
Oh yeah, are we going to be writing one piece of code for the validator and one piece of code for whatever this step 2 is?
I mean, they're in separate functions, but they're in the same file.
Same file, but
Yep.
it's 2 functions.
Yep.
Right?
Yep.
And what's step 2 called?
The step 2 was your next choice, right?
Oh.
Yeah.
Okay, so-
Configuration chooser.
Oh,
Right.
okay,
Yeah.
so-
Function 1, validation. Function 2, give me configuration. Any valid configuration that you have not tried already. And again, if you give me one that I've already tried already, it checks for that and says, no, please try again. So the only thing I caution you there is if you are using any sort of randomized or deterministic processes that do not realize that you might hit the same thing more than once, you will need to fix that so you don't get stuck. Right. So I have seen people have bugs where it's like, oh, well, I do this in this particular order, and then I produce this. And it's like, well, yeah, but you wrap back around to the same point, and you keep proposing the same thing indefinitely. Obviously, it's not gonna make any progress. Yeah. Yes. Then your validator should return false. So if your validator doesn't work and returns true for something where it should be false, one of two things will happen. Either The simulator will say, I don't know what the heck you wanted me to do. This configuration makes no sense. Your L1 is bigger than your L2. I refuse. And you will notice that by the fact that, well, the log files for that run are empty because the simulator did not run. You'll understand pretty quickly if you look at the logs that you have completely invalid data, right? It'll just go, right? You cannot have 0 as your joules or seconds, right? So you get some return zeros, right? So there are things that you can look at from a debugging perspective. You'll understand that things failed. There's some warning messages that'll pop up about the failure. If you run off the end of the table with a thing that the simulator will understand but is invalid from the specifications, then go look in your log files. When you run off the end of the table, you will usually see values that are many orders of magnitude different than all of the other values you are seeing. While there is variation in this metric across the different configurations, there are not 11 orders of magnitude of variation across this metric. All right, if you see something that is literally 10 to the 11th times worse, that's your bug, not you have found the worst possible processor, right? Okay, I will be having office hours next week as well. They will not be at exactly the same times. I will post them. I will see you all. Take care.